This isn't another incremental improvement or theoretical breakthrough that lives only in academic papers. This is the moment quantum computers stopped being expensive curiosities and became genuinely useful scientific instruments. Google's quantum team just achieved something that sounds impossible. They ran an algorithm on their Willow chip that completed calculations 13,000 times faster than the world's most powerful supercomputers. But here's what makes this truly revolutionary. This is the first time any quantum computer has accomplished something verifiable that definitively surpasses classical computing. And that single word, verifiable, changes absolutely everything. Let's unpack what verifiable actually means, because this distinction separates genuine scientific progress from impressive-sounding demonstrations. When something is verifiable, you can replicate the experiment on any quantum computer of comparable quality and consistently get the same results. You can even validate those results against physical nature itself through traditional laboratory experiments. Before this breakthrough, quantum computers were essentially performing elaborate parlor tricks, impressive demonstrations that we couldn't independently confirm. They were solving problems specifically designed to showcase quantum advantages, but we had no reliable way to verify whether the answers were actually correct. It's like someone claiming they can solve impossibly complex puzzles in seconds, but never showing you the solution in a way you can check. This breakthrough eliminates that uncertainty completely. To understand why this matters so much, we need to zoom out and look at the entire arc of human scientific discovery. Every major advancement in our understanding of nature has come from developing tools that let us observe things at new scales. We started by studying plants and animals with our naked eyes. Then microscopes revealed the hidden world of cells. Later, we discovered the molecules that power those cells. But here's the fundamental problem that's haunted scientists for centuries. Nature's complexity has always exceeded our tools' capabilities. There are questions about how the universe works that we simply cannot answer using classical computers, no matter how powerful we make them. That's precisely why quantum computers were conceived in the first place, to break through that computational barrier and give us the power to answer profound questions about reality itself. But until now, quantum computers have been stuck in what scientists call the doing science phase. Researchers were studying quantum computers themselves, trying to understand how to build them, how to make them work reliably, how to fix their fundamental errors. Today, that changed. Quantum computers have graduated from being the subject of study to being the instrument of study. They're now being used to investigate nature itself, to probe the quantum systems that govern everything from molecular structures to exotic materials. This is the equivalent of the moment when telescopes stopped being experimental devices that astronomers were figuring out and became the standard tool for discovering new planets and galaxies. So what exactly did Google's team accomplish? The algorithm they developed is called quantum echoes, and the concept is beautifully elegant. Think about how bats navigate using echolocation. They emit sound waves, listen for the echoes bouncing off cave walls, and use that information to build a mental map of their surroundings. Or consider how submarines detect underwater objects using sonar pulses. Google essentially created the quantum equivalent of echolocation. They took an array of qubits on the Willow chip and ran a precise sequence of operations forward through time. These operations are called quantum gates, the fundamental manipulations that control qubit behavior. After running these operations forward, they introduced a tiny disturbance into one qubit, like the butterfly effect playing out in a quantum system. Then they ran the exact same sequence of operations backward, essentially reversing time for that quantum system. The magic happens when the forward and reverse signals interact with each other. They create interference patterns, quantum echoes, that reveal hidden information about how the quantum system functions at its deepest level. What they're measuring is something called an out-of-time order correlator, or OTOC for short. This arcane-sounding term describes something fundamentally important: how different parts of quantum systems interact with each other across both time and space. It measures how information spreads and propagates through quantum systems, revealing connections and correlations that are completely invisible to traditional measurement techniques. Now, you might be wondering, if this technique is so powerful, why hasn't anyone done this before? The answer reveals just how technically impressive this achievement actually is. The quantum echo signals researchers are trying to detect are incredibly faint. Imagine trying to hear someone whispering your name in a packed stadium during a rock concert with terrible acoustics. That's the challenge. Historically, measuring out-of-time order correlators in large quantum systems has been one of the grand challenges in quantum physics. The signals you're searching for are buried under mountains of quantum noise and computational errors. You need hardware that's accurate enough to extract meaningful data from absolute chaos. This is where Willow demonstrates its revolutionary capabilities. The chip features quantum gates with accuracy levels that other quantum computers simply cannot match. Google built Willow using superconducting integrated circuits that offer precision that seemed impossible just a few years ago, but they didn't just rely on hardware quality, they also developed sophisticated error mitigation techniques. Rather than trying to brute force their way through the noise, they strategically reduce it using clever algorithmic methods, allowing the important signals to emerge clearly from the background static. The speed of these measurements is equally critical. They can complete milliseconds of quantum measurements in under 1 minute. That rapid data collection is essential because you need massive volumes of data to confirm your results and filter out random noise. Here's a statistic that should make you stop and think. Over the entire project, Google's team performed 1 trillion measurements. 1 trillion. To put that in perspective, that represents a substantial fraction of all measurements ever performed on all quantum computers combined throughout history. This wasn't a quick demonstration or a proof of concept. This was legitimately one of the most complex quantum experiments ever conducted by anyone, anywhere. Now let's get to the practical applications, because this is where it becomes clear why this matters beyond the laboratory. You're probably familiar with MRI machines. They've revolutionized medical diagnostics by letting doctors see inside the human body without surgery. The underlying technology is called nuclear magnetic resonance, or NMR spectroscopy. Scientists use NMR to determine the precise shape and structure of molecules. Why does molecular shape matter so much? Because structure determines function. The shape of a protein determines how it works in your body. The structure of molecules in a battery determines how much energy it can store. The architecture of new materials determines their properties. If we want to design better medications, more efficient batteries, or revolutionary new materials, we absolutely must understand molecular structure in complex environments with high precision. The problem is that NMR has inherent limitations. It's an incredibly powerful technique, but there are things it cannot see and distances it cannot measure effectively. Google partnered with researchers at UC Berkeley and used quantum echoes to predict the structure of 2 different molecules, one containing 15 atoms, the other containing 28 atoms. They then verified their quantum predictions using an actual NMR spectrometer in the laboratory. The results were stunning. The quantum computer's predictions didn't just approximately match the experimental data, they matched perfectly. But here's the truly exciting part. Quantum echoes also revealed structural information that isn't accessible through traditional NMR techniques. It can measure longer atomic distances than current methods allow. It's accessing data that conventional techniques simply cannot reach. This is enormous because it means quantum computers aren't just replacing existing tools. They're extending our capabilities, showing us things we've never been able to see before. It's the difference between getting a slightly better telescope versus suddenly being able to see in infrared and ultraviolet wavelengths that were completely invisible before. Let me explain why molecular structure understanding is such a transformative capability. It touches virtually everything in modern science and technology. In pharmaceutical development, you need to know exactly how a potential medicine will bind to its biological target. If you're designing a drug to fight cancer, you need to understand the precise 3-dimensional shape of cancer cell proteins, so you can design a molecule that fits into it perfectly, like a key into a lock. Right now, that process is phenomenally expensive and time-consuming. Pharmaceutical companies essentially synthesize hundreds or thousands of potential drug candidates, test each one experimentally, see what works, and iterate based on results. It's trial and error on a massive, costly scale. If quantum computers can accurately predict molecular structure and interactions, you could simulate the entire process computationally before ever synthesizing a single molecule in the laboratory. You could design the drug using quantum simulations, verify it will work as intended, and then manufacture only the candidates you know will succeed. That could compress years of development time into months and save billions of dollars in research costs. In materials science, the same principles apply. Want to design a battery with 10 times the energy density? You need to understand exactly how molecules in the battery components interact at the quantum level. Want more efficient solar panels? Same principle. Better superconductors for quantum computers and fusion reactors? You need to understand quantum interactions at the molecular level. The shape and dynamics of molecules are absolutely foundational to chemistry, biology, and materials science. Better tools for understanding molecular structure means exponentially faster progress in biotechnology, renewable energy, nuclear fusion, essentially everything. This breakthrough is categorically different. This is what scientists call verifiable quantum advantage with a clear path to real-world applications. That phrase contains three critical components. First, it's demonstrably faster than classical computers at something genuinely useful, not an artificial benchmark. Second, the results can be verified and repeated. You can run this algorithm on any comparable quantum computer and get consistent answers. You can validate results against physical experiments. Third, it directly enables real-world applications we actually care about. Before this, quantum computers were solving problems we specifically created for quantum computers, things like random circuit sampling that demonstrate quantum behavior but don't have practical applications. This is different. This is probing nature itself, understanding molecules, studying exotic quantum materials, potentially even modeling aspects of black holes and other extreme physics. The verification aspect deserves deeper exploration because it's such a crucial breakthrough. The fundamental problem with previous quantum computing achievements was verification. How do you confirm the quantum computer actually did what it claimed? If a quantum computer solves a problem that would require a classical computer 10,000 years to solve, how do you check whether the answer is correct? You can't run the classical computation to verify it. That would take 10,000 years. It's analogous to someone claiming they calculated the trillionth digit of pi mentally. Even if they give you an answer, how would you verify it without performing the entire calculation yourself? With quantum echoes, verification happens through multiple independent methods. You can run the algorithm on another quantum computer and check for consistent results. You can compare predictions to physical experiments exactly as they did with NMR spectroscopy. You can even verify certain properties of quantum systems against what we know from established quantum theory. This repeatability and cross-verification is absolutely crucial. It's what separates a genuine scientific experiment from a one-time demonstration. It's what makes this approach scalable. Think about the implications. If every quantum computation requires verification through some external method, that creates an impossible bottleneck. But if quantum computers can verify each other's work, and if those results can be cross-checked against physical reality, you're building a foundation of trust in quantum computing results. That's what transforms this from simple quantum advantage into verifiable quantum advantage. The verifiable component is just as important as the advantage itself. Google's research team used a perfect analogy to describe this moment. When we invented telescopes, we suddenly could observe planets, stars, and galaxies that had always existed but were completely invisible to naked eye observation. When we invented microscopes, we discovered cells, bacteria, and microorganisms that had always been there but were too small to see. This is the same kind of transformative moment, but for quantum systems. Quantum echoes functions like a molecular microscope, or perhaps more accurately, a quantum scope. It's an instrument that lets us observe and measure measure phenomena that have always existed but were inaccessible using previous technology. The quantum interactions inside molecules, the way information propagates through quantum systems, the correlations between distant parts of a material, these things are happening constantly in nature, in your body, in the materials surrounding you, everywhere. But we couldn't measure them accurately before. Now we can. Google is projecting real-world applications within 5 years. That might sound optimistic, but it's actually quite reasonable given this breakthrough. They've already demonstrated the core algorithm works. They've verified it against real experimental data from NMR spectroscopy. They've shown it runs 13,000 times faster than classical computers. What remains is scaling the approach and refining it for specific applications. That's challenging engineering work, but it's a known path forward, not fundamental research into unknown territory. Consider where quantum computing stood just 5 years ago. In 2019, researchers were demonstrating quantum supremacy on artificial problems. Today, they're running verifiable algorithms on real scientific problems and matching experimental results perfectly. The progress has been exponential. Willow solved the 3-decade-old error correction problem. Quantum echoes demonstrated the first verifiable quantum advantage. Each breakthrough builds on previous achievements and accelerates progress further. Within 5 years, we could see quantum-enhanced drug discovery platforms, quantum simulations for battery material design, quantum models of chemical reactions for industrial catalyst development. The future just arrived ahead of schedule.